Okay, this is lesson 6. It's called the generator effect and Lenz's law. So the first bullet here is something that we already know. Throughout the unit, we have been talking about how currents, or moving electric charges, they're really the same thing, induce magnetic fields. The word induce means cause. So we know when we have an electric charge that's moving, a magnetic field is created around that charge. The second bullet is something new, and it's sort of the opposite of the first bullet. So a scientist named Michael Faraday discovered that if you have a moving or changing magnetic field, that can cause a current. So first thing we need to look at is, what is a changing magnetic field? Well, it's basically a magnetic field that is getting stronger, or a magnetic field that is getting weaker, or a magnetic field that changes direction. So it's not constant. The magnetic field is getting stronger, weaker, or changing direction. So what Michael Faraday discovered, again, is that a changing magnetic field induces, so causes, a current in a nearby wire. So to illustrate what I mean by this, pretend that the pink marker is a wire, okay? And pretend that this blue marker is a magnet. If I take the blue magnet and I wiggle it around near the pink wire, well, the magnetic field of this blue magnet is changing direction right now, just because I'm moving the magnet around. That's making the magnetic field around it change too. And the changing magnetic field will cause a current to start to flow through the wire here, okay? The important thing is, earlier in the unit, when we wanted to have a current, we had to hook our wire up to a battery. This is different because the pink wire is not hooked up to a battery, and so it's not a battery causing the current to flow. It's actually the motion of this magnet that's nearby that's causing the current to flow. So Faraday decided to call this electromagnetic induction. Sometimes you'll just see induction. So electromagnetic induction and just plain old induction are the same thing. Or sometimes it's also called the generator effect. So really important, only changing magnetic fields induce currents. If you have a steady magnetic field, you will not get a current in any wires that happen to be nearby. So as I said, induction can also be called the generator effect. So this is just repeating the same thing again. The motion of a magnet can cause a current. The reason that it's called the generator effect is this is actually how generators work. So when you think of a generator, you probably think of like a backup power source. So you might have a generator in your house because, for example, if the power goes out, you can use a generator to actually create electricity for you. And that way you can charge your phone even when the power is out. Okay, or another example of a sort of simple generator is a hand crank flashlight. So this is a flashlight here. It actually does not have a battery inside. How it works is when somebody turns the crank, the light turns on. So what's happening in here is that there's actually a magnet with some wire around it. When you turn the crank, you're turning the magnet inside. That moving magnet causes a current in the wire, and then if the wire is attached to a light bulb, the light bulb can light up. So a generator is really anything where you're starting with motion energy, right? When I turn a hand crank, I'm inputting motion energy, and then that motion energy is being turned into electrical energy, even though there's no battery or power supply involved. So remember in the last lesson, we talked about the motor effect. The motor effect and the generator effect are really opposites. So generator effect takes mechanical energy, which is motion energy, and turns it into electrical energy. The motor effect does the opposite. It takes electrical energy from a battery and turns it into motion or mechanical energy. So we also have this thing called Lenz's law. So Lenz's law is for finding direction, specifically the direction of the induced current caused by a changing magnetic field. Or another way to think about that, Lenz's law is for finding the direction of the current made by the generator effect. So this example here, we will use this to illustrate what Lenz's law is. So it says the north pole of a magnet is pushed into a coil. So here's the magnet, there's the north pole. This is a coil, otherwise known as a solenoid. We want to know which way electrons are going to flow through the wire over here and which end of the wire is positive. So the important thing about Lenz's law is that when we use Lenz's law, motion is opposed. So we should probably write that down. Lenz's law, motion is opposed. So here, the magnet is moving, okay? This arrow here shows us the direction of motion. So somebody is trying to move this magnet to the left. What will happen is the solenoid will try to oppose that motion. The way to oppose the motion is by making this side of the solenoid north, because a north pole will repel the north pole of the bar magnet, right? That will make it harder for the bar magnet to move towards the solenoid. So if this side of the solenoid is north, then the other side of the solenoid is south. Okay, so Lenz's law, you oppose motion. And then, now that we figured out which end of our solenoid is north, we can actually use our solenoid hand rule, which is hand rule number 2, to figure out the direction of the electron flow. So because the question mentions electrons and electrons are negative, I'll use my left hand. And remember, the solenoid hand rule says you point your thumb towards the north pole of the solenoid. So at this point when I do this, I am completely ignoring the bar magnet. I no longer care about the bar magnet. I'm pointing my thumb to the right because I'm trying to point it towards this north pole that I drew in blue. Okay, now that I've done that, my fingers show me the direction of the electron flow. So the electrons are going around the solenoid like this. So across the front part of the solenoid, which is right here where I'm pausing, the electrons are flowing towards the top of the page. So the electron flow in the solenoid looks like this. There we go. So we can say here that the electron flow is from B to A. So we've just answered the first part of the question. Now it says which end of the wire is positive. So this is a little bit strange because we don't actually have a circuit here. So the electrons are not completing a circuit. What will happen is when the electrons leave B, they eventually end up at A and they just all collect at A. So there's an electron party going on at A. So what happens is because all of the electrons collect at A ends up being negative, and all of the electrons left B, so now B has a deficit of electrons, so B ends up being positive. So Lenz's law happens because of conservation of energy. So it's a consequence of the fact that energy is conserved. Electrical energy can't appear when I do zero work. So going back to this for a sec, if I am trying to move the bar magnet into the solenoid, I have to do work, right? So I have to actually push that bar magnet in. It's going to be difficult for me to do that because of the repulsion happening. Imagine for a second that this here, instead of being a north pole, imagine that this had been a south pole. If that was true, then I could just set the bar magnet down and I wouldn't have to touch it at all, and it would go into the solenoid because of the attraction there. If that happened, I would be doing absolutely no work. I wouldn't be putting any energy into the system, but then I would be getting a current in the wire. And you can't get a current or electrical energy from nothing, right? You don't get energy for free. You have to do some work, and then the work gets turned into electrical energy. So the reason that Lenz's law opposes motion is to make it so that you're not getting energy for free. Okay, so also going back to the example from a second ago, when we are doing this question here, there's actually sort of three things going on. So first of all, a current is induced in the coil of wire by the motion of the bar magnet. So here, the bar magnet was moving. We know that a moving magnet causes a current. So that's where the current came from. Okay, now we know from earlier in the course that when you have a current running through a solenoid, the solenoid becomes magnetic. So the fact that we got this current here is what caused us to have a north and a south pole. Okay, and Lenz's law says that the new induced magnetic field, so the induced magnetic field is the one inside the solenoid, that magnetic field opposes the original magnetic field from the bar magnet. Okay, let's try another one. So it's a very similar question. So it says, what direction is the electron flow in the coils if this time the bar magnet is being removed from the solenoid? So again, we're going to use Lenz's law, which means we're going to think about opposing motion. So here, this time, the motion of the magnet is to the right. Now, to oppose that motion, the solenoid has to actually make this a south pole because it wants to make it hard for the magnet to move away. So if the magnet's trying to move away, but at the same time the solenoid is attracting that magnet, then we will be opposing motion. So if this end is south, then the other end is north. Now that we've figured out where the north pole is, we need to use our solenoid hand rule to check the direction of the electron flow. So we're going to point our thumb to the north, and I shouldn't be doing it that way because that's my right hand. Let me try that again. So I need to use my left hand because it's electron flow. So thumb is pointing to the north pole of the solenoid. Remember, at this point, I no longer care about the bar magnet, but I do care about this north pole here, so I'm pointing my thumb towards it. Now I'm looking at what my fingers are doing, and my fingers curl in the direction of the electron flow. So across the front of the solenoid, which is this part here that you guys can see, the electrons are flowing to the bottom of the page. So if I draw in the electron flow, it looks like that. So the electron flow is from A to B. Okay, now it doesn't ask us this, but if it did ask us which end was negative, B is negative, A is positive, because B is where the electrons are collecting. Okay, we can also do Lenz's law for a straight wire instead of for a solenoid. So let's say we have a situation like this where we have two magnets and we have a wire that's traveling out of the page. So if my pen is the wire, somebody is moving the wire like this. Now, it doesn't actually matter whether it's the magnets that are moving or whether it's the wire that's moving. If one or the other is moving, induction is going to happen. So when this wire starts to move, electrons are going to flow through it. And we want to know which way the electrons are going to flow. When we do Lenz's law for a straight wire, we are going to oppose motion again. However, the hand rule that we're going to use is different. So we're actually going to use our third hand rule, okay? And so before I do that, I need to draw in the direction of the magnetic field. So the magnetic field, like always, goes out of the north into the south, okay? Now, if the wire is trying to move out of the page, to oppose that, we need to force it back into the page. So when we do our third hand rule, it's going to look like this. I'm going to use my left hand. I'm going to point my fingers in the direction of B, and I'm going to point my palm into the page. Okay, the reason my palm is pointing into the page is because the wire is trying to move out of the page and I am trying to oppose that. I have to do the opposite. Now, I look at what my thumb is doing. My thumb is pointing to the bottom of the page, and my thumb represents the electron flow. So that means the electrons in this wire are flowing like that towards the bottom of the page. And again, that electron flow is not because of any battery, right? It was because of the motion of the wire. Okay, this is an old diploma question. So a copper ring is suspended by insulating string. The north pole of a bar magnet is brought toward the ring. The approaching magnet induces an electron flow in the ring. So that's just saying because the magnet is moving, electrons start to flow through the copper ring because it's conductive. The interaction of the magnetic effects of the induced electron flow and the bar magnet causes the ring to swing. Okay, and it says the ring swings either away from or toward the magnet, and we want to know the direction of the electron flow at point P. So let's put this back for a sec. So here's what's happening. Okay, my hair elastic represents the copper ring, and then this marker represents the magnet. And I'm just going to hold the copper ring up like this so it's easier to see. So let's say that where the lid of the marker is, that is the north pole of the magnet. Okay, so when I bring the north pole close to the ring, the motion needs to be opposed. Now, this ring is just like a very tiny solenoid where one side of the ring can be north and the other side can be south. So either this side here is north or maybe this side here is north, and we need to figure out which one it is. So thinking about that, to oppose the motion, the ring needs to repel the bar magnet. So because this part of the bar magnet is north, that means that this side over here of the ring needs to be north. And that means the other side over here will be south. So because this is like a mini solenoid, now I'm going to do my solenoid hand rule, and with my left hand, I'm going to point my thumb towards north. Okay, now I can see that the electrons are flowing around the ring. So I'm just going to rotate everything so we can see it better. So north was up here. The electrons are flowing around the ring like this. Okay, so at point P, because the electrons are flowing like that, at point P, the electron flow is towards the bottom of the page. Okay, so we've answered part of the question. Now, the other part of the question was, does the ring swing towards the magnet or away from it? Well, what's happening is, if I put it back up like this, over here, this side of the ring is north, and this side of the bar magnet's north. You have a north pole approaching something else that's north. That means the ring is going to repel from the bar magnet, so it's going to swing away from it. So let's just pick out the answer. So it was away from, and then it was to the bottom of the page. So the answer there is B. Okay, last one. So which of the following is an example of electromagnetic induction? So this is just testing whether we know how induction is defined. Not anything can be called induction, okay? It's only induction when motion causes a current. So either a magnet moves or a wire moves within a magnetic field, and that motion makes a current flow in the wire. The only option here that matches what I just said is option D. So option D is the correct option.